Okay, good afternoon, everyone. Am I audible?
Yes, sir.
Yeah, okay. So, first 5 minutes, let me revise whatever we have discussed in the last class. Okay, and whatever which we have discussed in the last class, that is there in the PPT. You can go through this PPT. I'll give you. I'll share it with you, so you can go through this. So in the last class, we were discussing about transmission line. So transmission line was the medium, or you can say was the channel from between source and destination. So there was a energy transmission which is takes place through this transmission line. Like we are talking about microwave energy. So a microwave energy which is carried out through this transmission line from one point to the another point. And transmission line are having a distributed parametric network. So whatever the parameter like R, L, C lumped element which is there, so that is distributed throughout the transmission line. So you cannot extract R, L, C from one point. Okay, so you cannot go through, you cannot take R, L, C value at some particular point. You cannot find. So if this happens, that is called as a lumped parameter network. So we have the current as well as a voltage, okay, which is having magnitude as well as a phase over its length. Okay, so if you go through the current and voltage equations, and if you want to solve for the solution of the wave inside this transmission line, and you want to do the analysis, so you can have two ways. One way is having the Maxwell's equation, and you can solve for the Maxwell's equation, and you can go through and you will find the wave equation, which is traveling, the wave which is traveling inside the transmission line. Another way is using the distributed parametric analysis. So you can go through that way also. So the difference in the both way is if you want to take the distributed parameter network, so there that will have we will have the two variable, like one is the space variable and another will be the time variable. And if you go through the Maxwell's equation, so there will be three space variable like x, y, z component, and will have the time variable. So better to do the analysis, or easier way to do the analysis is the distributed parametric network. So physical dimension of the transmission line may be a considerable factor of wavelength or multiple wavelength in size. So what is this physical dimension? Physical dimension means it is the length which is there from the source to the destination, the length of the transmission line. That is called physical dimension of the transmission line. And it will be a considerable factor of wavelength. Why so? Because of the transit time effect. Okay, so I'll again will go very quick. What is transit time effect? But before going to the transit time effect, we have different types of transmission line. Like we have a parallel wire transmission line. So parallel wire, which is shown here, you can see that there is a twisted two wire, and both the wire will be in parallel. Okay, and this two end will be connected to the load. Okay, these two ends will be connected, that is called parallel wire. And for the analysis purpose, for the distributed parametric network, we'll take this parallel wire network, and we'll do the analysis. This is a simpler transmission line, or this is also called as a conventional transmission line for the microwave frequencies, and that was used for the antennas. Okay, so previously we were using in the rural area, or maybe urban area also, but in the rural area mostly we were using this type of parallel wire for the Yagud antenna. So And we have nowadays we are using this coaxial cable in the TV cable. You can also TV. This is also called as a TV cable that is connected from parabolic dish antenna to the setup box. So this is called coaxial cable. Okay, another is we have this the micro strip line. So this is micro strip line. Okay, so having the strip line which is connected on the one side, one side of the you can say strip, one side of the line, and another side we have one uh, mm, layer of conducting layer, and in between we have a dielectric material. So we will see this type of configuration also in the next class. So we'll see few types of transmission like microstrip transmission line, strip lines. Okay, so different types of transmission line we will see in the next class after the analysis of this transmission line, mathematical analysis. Next, we have rectangular waveguide. This is waveguide is also called as a transmission line. Okay, but there is a few difference between waveguide and transmission line. We will see, but this is also called as a transmission line. Okay, we have a circular waveguide. So different types of waveguide we have already seen. Now we will see what is transit time effect. So transit time is called as a TR, and time we know time is nothing but it is a time. Transit time means it is the time which is taken for the wave to travel from source to the load. That is from source side to the load side. So okay, so the time required. So time required means suppose we have a distance from source side to the load side is Z. Source side to the load side is Z, and we have a wave which is having some velocity that is called V. So the transit time will be seen as Z upon V. Z is equal to length of the transmission and V is equal to velocity of the wave. So any signal which cannot be traveled with infinite velocity, or you cannot say infinite velocity, that V cannot be infinite. So V cannot be infinite and V cannot be zero. So this velocity should be some finite value. If this becomes zero, that means there is no wave which is traveling from source to the destination side. So we can say the wave which is will have some finite velocity. So if the wave is having some finite velocity and Z is having some finite length, so transit time will be some finite value. So transit time should not be equal to zero, and that should be finite. So let us consider some voltage which is present at this side, source side, and the voltage which is present at the load side is VB. So this is VA and this is VB voltage potential at this point. So there would be potential difference between point A and point B. So that means if there is a potential difference, that means there is a transit time which is there. So the time required for the wave to travel from this A to B. So that means the potential difference. If this VA and VB is equal, then we can say there is no potential difference at all. So there is no transit time. So practically it is not possible. So practically this will be there. VA should not be equal to VB. That means there will be a potential difference. So to avoid this transit time effect, we need to take some signal, some wave. Wave is like this way. So wave will have some time period that is called capital T, which is called 1 by F, 1 upon frequency. So wave will having some time period. So to avoid this transit time effect, you need to send your signal. You need to send your signal one pulse which is coming, one pulse which is going to the load. So as soon as this cycle completes at this point, before completion of this cycle, one wave, another wave, you can say this should reach the load side. So that means within one time period, within one time period, you should reach the load side. Okay, so that means your T is equal to the time period of the signal. So that means we can neglect TR if T should be greater than transit time. So that means if you are sending your signal at this point. So you should reach at load side before coming to this point. Before coming to this point, that means the transit time should be less than, much less than, or less than this time period of the signal. So that means if t is equal to t should be greater than tr. So this capital T should be greater than z upon v, because tr is nothing but z upon velocity. So z is the length of the line and v is the velocity. So if you say time period is nothing but 1 upon f, so 1 upon f should be greater than z upon v. And if you take this v this side, so v upon f should be greater than z. V upon f is nothing but will have this as a wavelength. Okay, so velocity upon frequency is nothing but wavelength. Wavelength should be greater than z. So if the wavelength of the signal is greater than length of the transmission line, we can say transit time effect can be neglected. Okay. So transit time effect has to be taken into consideration when lambda is comparable to z, or lambda is greater than z, or lambda is less than z, or you can say it is comparable to z. So that will be a major drawback for this transmission line. Okay, to carry out the wave. So now the conventional two-conductor transmission line are commonly used for the transmitting microwave energy, and to have the maximum efficiency, line should be properly matched. So properly matched means whatever the load you have, ZL, maybe load is having some impedance ZL, and this line, the transmission line which is having the characteristic impedance Z0. So Z0 should be matched with the load line, that is called ZL. So if this is matched, maximum power transmission will be takes place. Okay, and you can also say the maximum power theorem, maximum power transfer theorem we can apply here. Okay, so to have the maximum efficiency of the transmission line, so it should be properly matched. That means characteristic impedance Z0 should be properly matched with the ZL. Okay, now if we can say a transit time effect, if the transit time effect is neglected, we can apply Kirchhoff's law. But due to transit time effect, we cannot apply Kirchhoff's law. We cannot apply the low frequency analysis. Okay, so this should be avoided. Transit time effect should be avoided, and this should not be significant. Okay, transit time effect should not be significant. Otherwise, our efficiency will not be good. Okay, so we'll not get maximum efficiency, or will not utilize the maximum efficiency of the transmission line. Okay. Now, if you go through the transmission line equations, okay, or solution of the transmission line, it will be looks like the wave equation which we have already discussed in the wave guide. Okay, so we can go through this transmission line equation, and we will try to see how the wave equation is look alike in transmission line. Okay. So now we have a transmission line which is shown here, We'll see one by one. Okay. So transmission line can be analyzed either by solution of Maxwell's field equation or by the method of distributed circuit theory. So Maxwell's equation will have three space variable, like one time variable like x, y, z, and of course we have a time. Okay, and distributed circuit theory we have z and t. So one space variable and one time variable. So now here, this is the schematic circuit of conventional two conductor or two wire transmission line, two parallel wire transmission line, which is shown here with the constant parameter R, L, G, and C are shown here. What is this resistance, conductance, inductance, and capacitance which come into the picture? So we'll have resistance. Okay, so resistance due to the wire which is used for the transmission line, and inductance which is due to the current which is flowing through this transmission line. So current means which is generated from the generator, the electric field which is generated from this one, this generator, and this electric field causes magnetic field, and magnetic field causes the current, and the inductance will come into the picture. and the capacitance which is due to the parallel wire, the two wire which is there, so this capacitance will come due to the wire, parallel wire which is used, and G which is due to the leakage current. So leakage current, some leakage current will be there, so to represent this leakage current we use G here. Now your question will be why we have used R with the delta Z, L with the delta Z, G with the delta Z, C with the delta Z. All these is multiplied with the delta Z. So why so? So if you see, this is the distributed parametric network. So we cannot take RLC, we cannot extract RLC at directly. So to have this RLC, even G, uh, so to have this, we need to take the small delta Z element, and under some assumption, we just take a small delta Z element from A to B throughout this transmission line. We just take delta Z element, and in this delta Z element, we take out as a, we have a resistance, we have a inductance, we have a conductance, we have a capacitance, and all these will be repeatedly, it will be there. So this hyphen means it is a continuous line. Here also it is a continuous line. Okay. So in this we have extracted this RLGC element. This is the elementary section of the transmission line, and all these resistance, inductance, which is in association, or which is in connection with the delta Z. So just we have multiplied with the delta Z. So delta Z is a small element, which is a small element of the transmission line, and we just multiply resistance with this delta Z, inductance with delta Z, and similarly we have a conductance G with the delta Z, okay, and C with the delta Z. And the voltage which is present here at point A is represented at Vz comma T, because we are doing the distributed circuit theory analysis. So we just take two variable, there is Z and T. So Vz and Vz comma T at point A, and at point B it will be some voltage at Vz plus delta Z comma T, because the time is also changed, but we just ignored, because it is a very small element, that is delta Z. So time, if you want, you can take T as a T plus delta Z also. So this can be V Z plus delta Z comma T plus delta T. So this is also exact analysis. If you want to take that, that will be there, but we ignored, because delta T is very less value, even though delta Z is also very small value. But for the analysis purpose, we have taken this delta Z. But in the later stage, we will take delta Z as a limit. We will apply, and limit delta Z tends to 0. We will try to apply limit delta Z tending to 0, because delta Z is very small value. Now all these, this resistance, capacitance, inductance, and conductance, which is represented in the unit, you can say it is having resistance is having its own unit, that is called ohm, and which is having the per meter. So ohm per unit length, that is means resistance per unit length. This is called resistance per unit length. The ohm per meter. There's a Faraday per meter, Henry per meter, Mho per meter. So all these is in the reference with the per unit length. So it is represented per unit length. Now you can see we are having the current which is moving inside this small element, that's called Iz comma T, and coming out from this is Iz plus delta Z comma T. Again you can say T plus delta T, but we have taken the T. So this is for the simplification purpose. Iz comma Iz plus delta Z comma T. Now we will try to take the KVL and KCL, Kirchhoff's current law and Kirchhoff's voltage law. Under some assumption, we will try to apply this Kirchhoff's voltage law as well as the Kirchhoff's current law. So if you apply Kirchhoff's voltage law, so in the central loop, means this loop we want to apply. So this loop is having I want to take this as a, okay, and this is this one, and there's a capacitance which is coming here. Just take this, okay, and this is the point which is having Vz comma T, and this is called R delta Z, L delta Z, and we are having G delta Z, C delta Z. So now this point is having some voltage. This is called VZ plus delta Z comma T. Now the current which is coming out from this point, it's called I Z plus delta Z comma T, and current entering to this point is nothing but B, and this is called IZ comma T. Now, if you apply KVL, the Kirchhoff's voltage law, so that will be nothing but will apply from this point. So this can minus Vz comma T plus Iz comma T into R delta Z, V is equal to IR plus L delta Z del Iz by dt, because L di by dt will be there. So that's what we have written, minus Vz comma T plus L delta Z del Iz comma T divided by delta T plus R delta Z Iz comma T plus Vz plus delta Z comma T. So just simpler it is apply. Just take it out from here, and it is come to this point. So it is again making a loop. So KVL, KVL can be applied inside any loop. So just we have applied at any at this loop, and we have taken all the voltage we have written. So this is the voltage which is for this one, and this is the voltage due to this inductor, and this is the voltage due to this resistance, and this is the voltage at node B. So now if you rearrange this one, you take this Vz plus delta Z comma T minus Vzt one side, and all these two is this side, so this will come negative sign, and you take this delta Z, just divide delta Z on both side, so this will become Vz plus delta Z comma T minus Vzt divided by delta Z, and this delta Z will out from this point, and this term also delta Z will be out. So now after taking this delta Z here, or you can say dividing delta Z on the both side, just apply limit delta Z tending to 0. So if you apply delta Z, limit delta Z tending to 0 in the both side, so this side we don't have any delta Z, so no need to apply. If you want, you can apply. So just apply limit delta Z tending to 0 on both side. So this will become limit delta Z tends to 0, Vz plus delta Z comma T minus Vz plus Vz comma T divided by delta Z. What is this? This is nothing but a differential function. Differential function, you might have studied in the 12th class, 12th standard. This is nothing but a differential function. So this is nothing but a differential function. So we have written partial differentiation. Why it's so partial differentiation? Because we have a two variable, and it is in terms of delta Z. So we should write partial differentiation with respect to Z. So this will become del upon del Z Vz of T, or del Vz comma T divided by del Z. Which is equal to minus L del Iz comma T divided by del T minus R Iz T. Now, if you take this in a frequency domain, if you want, you can write. So this can be del upon del T can be written as a j omega, very well. So del upon del T can be j omega. So I'll just write this del upon del T as a j omega, and del by del Z will be written as it is. So this can be written as minus j omega L Iz comma T minus R Iz comma T. So if you take minus outside, and you take Iz comma T as a outside, so this will become R plus j omega L. So this is del Vz comma T divided by del Z is equal to minus R plus j omega L Iz comma T. This is equation number 1. Now we will see the second equation. I will try to find the second equation after having the KCL at node, this node. So we'll try to take this KCL at node B. So what is this KCL? KCL means the current entering at a particular node, we should be equal to all the current which is entering at particular node, which should be equal to the current which is coming out from the node. So we will take this entering node, the current which is coming to this node as Iz comma T. So this is entering, means we have taken the assumption that entering is negative. So minus Iz comma T, and this the current due to this capacitor, and current due to this this conductance will be coming out of the node. So the current which is coming out to this node, so this is nothing but G delta Z into VZ plus delta Z into the potential at this point. So potential at this node will be applied to this one also. So you know what is this capacity, what the current in the capacitance. So current in the capacitance C dV by dt, I is equal to C dV by dt. So C delta Z into d VZ plus delta Z comma t divided by del t. So just we have written minus Iz plus t, Iz comma t, and the current which is coming out from this one, so we written as a plus sign. So plus Iz plus delta Z comma t, and this can be written as G delta Z Vz plus delta Z comma t, and plus C delta Z del Vz plus delta Z comma t divided by del t, which is equal to 0. So now we'll try to take this term as a one side, and this term as a another side. So just I take Iz plus delta Z comma t minus Iz t to this side, and I'll let you know this what is delta Z, and these two term is this side, and just divide whole term both side with delta Z. So delta Z will be omitted, and this will be associated with this one. Okay. Now again, we will apply limit delta Z tending to limit delta Z tends to 0. So what will happen? This term will be as it is, and this can be written minus G V Z comma t, because delta Z is tending to 0. So this will be omitted. This will be omitted. So this can be written as minus C del upon del t V Z comma t. So that's what it is written here. So applying limit delta Z tends to 0 on both sides, so we'll get del Iz comma t divided by del Z. So this can be written as, this whole term can be written as del Iz upon del Z. Okay, del Iz comma t. So del Iz comma t divided by del Z, which is equal to minus G Vz comma t minus C d del Vz comma t divided by del t. Now del by del t can be written as j omega. So in frequency domain, so I can write here this as a, and we'll take Vz comma t as outside. So this can be written as G plus j omega C Vz comma t. So what we understood from this equation, what we understood from this two equation. Okay, so these two differential equation. So now if you go through the rectangular waveguide analysis. Okay, if you go through the rectangular waveguide analysis, wave equation analysis, I'll go through the PPT very quick. Okay, so similar wave equation which we had got in the rectangular okay waveguide. Okay, 1 minute. See, yeah, here only. So in the rectangular waveguide, while we are solving the differential equation for the rectangular waveguide, so we had got here, you can see 1 minute. Yeah. One minute. Yeah, the wave equation which we had got. Yes. So you can see the wave equation which we had got here, del S square E is equal to gamma S square E. So if you take in the Laplacian form, that will be del operator in Laplacian form. You can say double differentiation with respect to the dimensions, space dimension. So that will become, if you are taking double differentiation of electric field, you are getting converted into electric field. But if you take in the single differentiation, like if you take curl E, I cannot write here. 1 minute. Okay, I'll write here. So if you want to take curl E, so curl E is nothing but we have curl E is equal to sigma E plus j omega epsilon E. So I'm talking about this sigma is equal to 0. So curl E is equal to j Okay, 1 minute. Huh? No, 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 no. It's wrong. 1 minute. Okay. So if you talk about curl E, so curl E is equal to j omega mu into h. So j omega mu into h means electric field is converted into magnetic field. So electric field is converted into magnetic field is a one-dimensional analysis if you want to do. So one-dimensional analysis means electric field which is converted into magnetic field. And if you want to take the magnetic field which is if you want to take magnetic field will be converted into electric field. So if a magnetic field is converted to electric field and electric field is converted to magnetic field, so the one dimension analysis can be taken. If you go through the two-dimensional analysis, two dimension is the sorry double differentiation. Okay, double differentiation if you want to take, or Laplacian operator if you want to take, the wave equation will come into the picture, and wave equation will give you the, if you want to convert to electric field will be converted to electric field only. So this equation is quite similar. Like this is a wave equation. So this is the wave equation. So transmission line is also carrying out the wave inside the transmission line. The wave is carried out. So the wave is carried out means we 1 minute. Okay, audible now? Audible?
Yes,
Am I
sir.
audible? Okay. Okay, so that means the wave which is carried out inside the transmission line, uh, through this wave equation, and by this wave equation, and this wave equation will be taken here, and the wave will be formed in this way. So now you can see we are getting the two equation, that is current which is differentiated in a space domain. A differentiate one differentiation in space domain will give you the voltage. Okay, voltage equations. So the current which is converted into voltage, that should be differentiated in a space domain. Like this, like voltage, if you want to differentiate in a space domain, that will give you the current in the current in the another side, with having some constant value. So now if you double differentiate equation number one and equation number two, so double differentiate with respect to z only, or space domain only. So del square vz comma t divided by del z square will give you the minus r plus j omega l, and this side we had iz comma omega iz comma t. So that will be again differentiated with respect to the space domain. Now again, if you want to differentiate this second equation with respect to z, so this will give you del square by del z square iz comma t, which is equal to minus g plus j omega c, and del vz comma t divided by del z. Now these two equation number 3 and 4, if we take these two equation and just substitute equation number 1 and equation number 2 in these two equation, so we'll give the wave, we will get the wave equation. So how this side will keep as it is. Now we know we have del iz comma t divided by del z, which is equal to minus g plus j omega c vz comma t. So just substitute here, and we will get this type of equation. So we'll get del square vz comma t divided by del z square, which is equal to r plus j omega l g plus j omega c vz comma t. And similarly we'll get del square iz comma t divided by del z square, which is equal to r plus j omega l g plus j omega c iz comma t. So if you take double differentiation in a space domain, you will get the same voltage equation. If you want to differentiate voltage equations, you'll get voltage equation only. If you will differentiate double differentiate in a space domain, the current, so you'll get the current equation this side. So now what is this r plus j omega g plus j omega c? Let us assume that this can be represented gamma square. So this is represented gamma square, which is equal to r plus j omega g plus j omega c, and this gamma can be written as alpha plus j beta. So this gamma is nothing but a propagation constant. So I'll let you know, I'll go through this propagation constant, okay, okay, later on. So this we assumed that it is a gamma square, so will comes out to be del square by del z square vz comma t, which is equal to gamma square vz comma t. That's what we have. Nothing. We got del square e is equal to gamma square e. Okay, and del square h is equal to gamma square h. That's called Helmholtz equation, or you can say the wave equation which we had got. So similar equation which we are getting here. Okay, because del square was nothing but del by del x, del square by del x square plus del square by del y square plus del square by del z square. So that was in three dimension, three space dimension, and here we are having one dimension. Okay, so this is the wave equation. This is the wave equation for the transmission line. Okay, or you can say this is the wave, the voltage and current wave which is traveling inside the transmission line. So now what should be the solution of this transmission line, solution of this wave equation? So this is a standard differential equation. Now if you want to find the solution for this, so the solution for voltage as well as the current will comes out to be V naught plus or some constant A e to the power minus gamma z plus B e to the power plus gamma z. So we have written V naught plus and V naught minus e to the power minus gamma z to the power plus gamma z. So this is simply we have written with respect to z only. We have just ignored the time variable. Okay, we will consider the time variable here, but the time being just ignore this time variable and try to write. So what is this v naught plus e to the power minus gamma z and v naught minus e to the power minus gamma plus gamma z? So what is the significance or what is the meaning of this equation? Okay, this is what is the meaning of this voltage and current equation. So this is nothing but some constant value. This is the amplitude which is taking care, but this is the wave equation, you can say, or this is the wave exponent which is responsible to carry out the wave from one point to the another point. So if we are having the e to the power minus gamma z, that means our wave is traveling in the positive z direction. And if this is this is the plus gamma z, e to the power plus gamma z, so that means our wave is traveling in the negative z direction. That's what it is written here. So if the wave is traveling in plus z direction, so your exponent will be e to the power minus gamma z. And if the wave is traveling in negative z direction, so it should be e to the power plus gamma z. So both cases both cases simultaneously it is not possible. Okay, because wave will either it is traveling at one time, it may be traveling in positive z direction, or it may be traveling in negative z direction. So both cases, both side traveling both sides simultaneously, it is not possible. So at one time it is traveling in one direction. But if you want to write the complete wave equation, so that will be written in this form. Okay, so this is the one of the wave which is traveling in plus z direction. This is the plus z direction, the wave which is traveling in negative z direction. Now similarly we have a current which is traveling, so current is also traveling in plus z direction as well as in negative z direction. Okay, so that means it is going to the incident wave, that is the plus z direction. So v naught plus, which is going to this side. Okay, and v naught minus, it is coming to the reflected wave, and reflected voltage or reflected wave, you can say, inside the transmission line, it is coming out from the load. Now, if you want to consider the time domain also, so if you want to consider time domain, it will be written in this form, and it can be written as V naught plus cos omega t minus beta z plus phi plus phi plus e to the power minus alpha z, because gamma can be written as alpha plus j beta. So if you want to write alpha plus j beta, this can be written as e to the power minus gamma z. So that will become e to the power minus alpha z, and into e to the power minus j beta. So and of course we'll have a omega t also. So omega t will be there. So omega t minus beta z will comes out to be a cos function, and that will give you the cosine function. That will be the wave which is traveling through this transmission line. Okay. Similarly, for the negative z direction, the negative z direction component will be there, and this is the positive z direction component. At one time, only one component will be there. Okay, so this is the wave equation which we are having. So you can correlate. You can correlate with the a rectangular waveguide also if you want to solve for the Maxwell's equation. So using the Maxwell's equation, we can also go through the wave equation. We'll get similar type of wave equation. Okay. Now we are having a characteristic impedance. So that was the solution of wave equation. Okay, but that was solution of wave equation inside the transmission line. So if I'll ask, okay, if I ask what is the or solve for the solution of wave equation in transmission line, so you should solve in this way using the distributed parametric analysis. Okay. Now we have a characteristic impedance. So characteristic impedance is represented Z naught, and which is having the unit as a ohm. Okay. So okay. So ohm, which is represented here. Okay. Uh, so what is the characteristic impedance? How we can find the characteristic impedance? So characteristic impedance or impedance, any impedance if you want to find. So you are having the voltage equation as well as the current equation. So V is equal to I into Z. So you are nothing but you can find V of Z is equal to I of Z into Z naught. So this Z is nothing but the length. Okay, Z is nothing but direction or space dimension. So if you want to find current, if you want to find Z naught, so Z naught should be equal to V of Z divided by I of Z. So that's how we will try to find out. So now we have the equation number 1, 9 and 10. I will try to differentiate with respect to Z. So 9, 10, which we have here, okay, V of Z, I of Z. So we'll try to differentiate with respect to Z, and we just time being just take the wave which is traveling in positive Z direction only. So we just ignore the e to the power plus gamma Z wala value. So just ignore that one, and this will give you del V upon del Z, which is equal to minus gamma V naught plus e to the minus gamma Z. So if you want to differentiate with respect to Z, so this minus gamma will come out here, and again here also minus gamma will come out here. So this is the equation for this one. Now we know del V upon del Z. What is the del V upon del Z? So del V upon del Z is nothing but minus R plus j omega L Iz. Okay, so we can write here, and this side already we have. So now we can find out I of Z. I of Z should be written as I of Z can be written as minus gamma or minus gamma upon minus R plus j omega L, and this will be written as V naught plus e to the minus gamma Z. So V naught plus e to the minus gamma Z can be written as V of Z. So that's why we have written V of Z. So if you want to write I of Z can be written as V of Z divided by Z naught. I of Z is nothing but V of Z divided by Z naught, or Z naught can be written as V upon I. So that means this Z naught can be written as R plus j omega L divided by gamma. So R plus j omega L divided by gamma, where gamma is equal to R plus j omega L and into G plus j omega C. So if you take this R plus j omega L, if you want to cancel out, so in the numerator we'll left with the square root of R plus j omega L, and denominator will left with the G plus j omega C. So Z naught comes out to be R plus j omega L divided by G plus j omega C. So this is the called characteristic impedance, and this characteristic impedance is nothing but a square root of R plus j omega L divided by G plus j omega C. So this is the characteristic impedance we have. Okay, so you can have this characteristic impedance. But okay, so if I'll ask a solve for the characteristic impedance for the in the transmission line, so you just take wave equation, you just take voltage equation. V of Z is equal to V naught plus e to the power minus gamma Z, and I of Z is equal to I naught plus e to the power minus gamma Z. And you can solve for by taking differentiation with respect to Z, and try to solve using this one. You can find out. Okay, now we have a propagation constant. This is responsible to carry out the microwave energy from source to the destination side. So this is the propagation constant. This propagation constant is gamma is equal to square root of r plus j omega l plus g plus j omega l, because gamma square we just assumed that gamma square is r plus j omega l, g plus j omega c. So gamma can be written as square root of r plus j omega l plus into g plus j omega c. Okay. Now this can also be written as alpha plus j beta. So you can find out alpha as well as a beta. We'll go through alpha as well as a beta. Okay, by having the binomial expansion. Okay, by taking j omega l outside, j omega c outside. So we'll let you know in the next slide. Next slide we have. Okay, so we can find out alpha as well as a beta. Why alpha beta is useful? Alpha is nothing but attenuation constant, beta is called phase constant. So phase constant is needed, phase constant is required to have the wavelength of the transmission line. So to find the wavelength of the transmission line, lambda is equal to 2 pi by beta, which is called wavelength of the transmission line, and beta is equal to phase constant, and vp is called phase velocity. Phase velocity is nothing but omega by beta, and this can also be written as lambda into f. Okay, so lambda into f, which is called phase velocity. Okay, now we have a few problems. So we have two problems. We'll try to see this problem. Okay, so the problem which is given here, the problem which is given here. Okay, so the current in transmission line is given as I of t is equal to 1.2 cos 1.5 into 10 to the power 10 t minus 80.3 z. Determine the wavelength, okay, comma the dielectric constant, phasor representation of the current. So how you can find? So this is the current which is given here. I of t is equal to 1.2 cos 1.5, okay, 1.5 into 10 to the power 10 t minus 80.3 z. Okay, that is the representation which is given here, current. Now this current can be written as I naught, or you can say I naught plus. Okay, see here it is given as a minus beta z, minus beta z, omega t minus beta z. So minus beta z is nothing but minus beta z is nothing but the wave is propagating in plus z direction. Okay, so I naught plus will be there, cos omega t minus beta z. Okay, so from this, that means that is wave which is traveling, or current wave, you can say current wave. Okay, current wave is traveling in plus z direction. Keep in mind always, if you have a negative z minus z, so that means the wave should be traveling in plus z direction, just opposite you should take. So now from this we can find omega, which is equal to 1.5 into 10 to the power 10 10 radian, okay, per second. Okay, now we have beta, which is equal to 80.3. Okay, so beta we got 80.3. So what should be the wavelength? We know wavelength lambda, which is equal to 2 pi by beta. So 2 pi by 80.3. So that comes out to be some 0.0782 meter. Okay, that will give you this value. Okay, now if you want to find dielectric constant, okay, dielectric constant. So how we can find dielectric constant? Dielectric constant is nothing, epsilon r, na epsilon r. How we can find epsilon r? So to have the epsilon r, first of all, we should go through the phase velocity. So we'll have phase velocity. Why phase velocity? I'll let you know. Okay, but please see phase velocity Vp. Vp is nothing but omega by beta. So omega is nothing but 1.5 into 10 to the power 10. Okay, divided by 80.3. Okay, 80.3. So Vp is comes out to be 1.88 into 10 to the power 8 meter per second. So phase velocity, already you know what is phase velocity. So we know that phase velocity is nothing but 1 by root under mu into epsilon. Already we have from the analysis from the starting, we know a phase velocity can be written as square root of 1 upon square root of mu into epsilon. Whether in that we have mu r into epsilon r. So let us assume mu r is equal to, let mu r is equal to 1. So from this we can have this Vp is nothing but this can also be written as, Vp is equal to C upon square root of mu into r, mu r. Why so? Because this can be written as 1 upon square root of mu naught epsilon naught into mu r into epsilon r. So 1 upon mu naught into epsilon naught is nothing but C. C is equal to 3 into 10 to the power 8. So from this we can find 1.88 into 10 to the power 8. Okay, and which is equal to 3 into 10 to the power 8 divided by square root of epsilon r. So from this we can find out epsilon r, which is comes out to be 2.78. Okay, 2.78. You can solve for this, go through this, and you will be able to find out. Okay, so epsilon r will be 2.78 value. Okay. Now we have another one which is given wavelength. We found out dielectric constant phasor representation of the current. So representation phasor representation of the current. Phasor representation of the current is nothing but we'll have I naught at an angle phase constant beta. So I naught is I naught plus we have 1.2. So 1.2 at an angle 80.3. That is nothing but beta. So that's called phasor representation, 80.3 angle. Okay. So that's what we have, phasor representation of the current. Okay. Correct. I hope it is clear. Any doubt? Okay. Now we have another question which is given here. A transmission line has the following parameters. R is equal to 2 ohm per meter. G is equal to the resistance, the conductance, 0.5 mho per meter. Frequency is given as 1 gigahertz, and inductance 8 nanohenry per meter, and the capacitance is 0.23 picofarad per meter. Calculate the characteristic impedance and propagation constant. Okay, so I'll try to find out characteristic impedance and okay, so characteristic impedance and propagation constant. So characteristic impedance, first of all, characteristic impedance Z naught. Okay, so Z naught, do you know what is the formula for Z naught? Z naught is nothing but R plus J omega L divided by G plus J omega C. So already you have all these data. You just try to find out the value. So you'll get R is nothing but 2 plus J omega is nothing but 2 pi F. No? So 2 pi into F is nothing but 1 into 10 to the power 9. So, and L is nothing but 8 nano Henry, 10 to the power minus 9, divided by this G is nothing but 0.5, okay, plus J omega 2 pi into 10 to the power 9, and we have C, capacitance is 0.23, pico means what? 10 to the power minus 12. So we have this one. Just try to find out. Okay, so we'll get some value. This will give you 2 plus uh, mm, 8 to the 16 j 16 pi, okay, divided by 0.5 plus 9 3 12 something. This will give you 10 to the power minus 3, 10 to the power minus 3, and 23 twos are 46. So J 0.46 pi into 10 minus 3. So try to solve. You will get to know. Okay, this will the value maybe just convert into phasor form. Okay, phasor form. and try to solve. Okay, otherwise you can have a calculator, you can take a calculator and try to solve. So this value is comes out to be 181.39 at an angle of 8.4 degree. Okay, or you will get 179.44 plus j 26.5. Okay, so that is the value you will get. Okay, that is in ohm na, because z naught we are calculating. Now similarly you can calculate for b, that's called gamma, propagation constant gamma. So gamma is called constant propagation constant, which is comes out to be r plus j omega l and g plus j omega c. So that comes out to be, I'll write directly here, r plus j omega l is nothing but 2 into j 16 pi, and this will be 0.5 plus j 0.46 pi into 10 to the power minus 3. So if you solve this, you will get to know this value comes out to be 0.277 at an angle of 79.31 degree. Okay, and if you want to calculate in a plus jb form, so this will give you 0.051 plus j 0.273. Okay, so that is the answer you will get. Very simple. Try to solve this. Okay, you can calculate. Okay, so what we have studied today. Okay, so we went through the overview of transmission line. Okay, we went through the transit time effect. Okay, which is a major concern for the transmission line, or conventional tubes also. Okay, so we'll see conventional tube, and we'll see again, we will see the transit time, transit angle effect, transit time effect, we will see. Next, we have transmission line equations, or solution for the wave equation in transmission line. So we went through the solution for wave equation in transmission line. We have taken one transmission line, and we just take a elementary section of the transmission line, delta Z, and we applied a KVL as well as the KCL, and by solving the KVL and KCL, we try to find out the solution of the wave equation, and wave equation will comes out to be this one, equation number 7 and 8, and the solution will be comes out to be equation number 9 and 10. So now after that we went through the characteristic impedance. Okay, and we also went through the propagation constant, and we went through the problems, few problems based on the based on what we have studied. Okay, so now we will go in a very quick 5 minutes, 5 more minutes I'll take. Okay, so we have different medium of transmission line, or you can say different types of different types of medium which is possible for the transmission line. So for that different mediums, we have a different characteristics which is there for the transmission, like we have a characteristic impedance, propagation constant, wavelength, phase velocity, and general solution of voltage and current for the transmission line that will be altered. Okay, although we have for the lossy line or for the general transmission line, we have the equation, and we will apply for the special cases. Like these are the special cases we have. Okay, here. So in that special case, we'll first we have first we have. Okay, 1 minute. Okay, first we have lossless transmission line. So lossless means there is no loss at all. Okay, lossless. So there is no loss. So that means loss occurred due to resistance, as well as this is a leakage. So this conductance. Okay, so resistance due to like I square R, or heating loss, or ohmic loss, you can say. So this is the due to the resistive loss. Okay, ohmic loss, and this is the G due to G. So G is called leakage current, leakage loss will be there. So to avoid these losses, we should have this resistance as well as a conductance. This should be zero for the transmission line. So if this is zero for the lossless transmission line, so all the equations which we have derived, or all the parameters which we have went through, that will be altered and formula will be changed. So we have we have a characteristic impedance that is called Z naught, which is equal to square root of R plus J omega L divided by G plus J omega C. So that comes out to be square root of L by C. Okay, because R which is equal to 0, okay, G which is equal to 0, J omega will get cancelled, so we'll get L by C. Okay, now similarly we have a propagation constant. So gamma is equal to square root of R plus J omega L, G plus J omega C. And if you take R is equal to 0, G is equal to 0, so J omega will come outside and we'll get square root of LC. So J omega root under LC will get gamma. And we know gamma is equal to alpha plus J beta. So that means alpha should be equal to 0 and beta will be J will be comparable and beta will be omega root under LC. That's called phase constant. Okay. So alpha is nothing but attenuation constant, attenuation constant. So that means there is a lossless transmission line, so there should not be any attenuation at all. So attenuation will not be there. But practically this lossless line is not possible. Okay, practical transmission line is not lossless. Okay, always there is a loss, or you can say there is a low loss in the transmission line, or low loss are there in the transmission line. So this is the ideal case. This is the ideal case. Okay, but practical case is low loss transmission line. Okay, so we'll see practical cases. So alpha is equal to 0, beta is equal to omega root under LC, and we have phase constant beta, which is equal to omega root under LC. What is the wavelength? Wavelength lambda is equal to 2 pi by beta, which is equal to 2 pi by omega root under LC. Similarly, we have phase velocity, Vp is equal to omega by beta, and omega get cancelled, and this Vp will become 1 by root under LC. And already you know Vp is nothing but 1 by root under mu into epsilon, or you can write C by square root of mu r into epsilon r. No, that can be written in this form. Now we have a voltage equation. So voltage V of Z can be written as V naught plus e to the power minus gamma Z, and V naught minus e to the power plus gamma Z. Similarly, we have a current. Current is nothing but I naught is nothing but V naught plus by Z naught, and this can be V naught minus by Z naught. Okay, e to the power plus gamma Z. So that's how it is written here. The gamma can be altered here. Gamma can be written as G omega root under LC. Previously it was R plus G omega L, G plus G omega C, square root of R plus G omega plus into G plus G omega C. But now it will become gamma is equal to G omega root under LC. Okay, so you can use this. Now we have a practical line. So practical, you can say practical transmission line. Practically it is low loss transmission line, or at microwave frequencies. This is the possible cases. So R will be, even though we can reduce, see this is not at all completely practical, but practically we can reduce this resistance and conductance, but although it will be there in a minute. Okay, so resistance can be reduced and the conductance can be reduced. So resistance can be reduced in this way. So if the R should be much less than omega L, and G should be much less than omega C. Okay, so omega already, you know, at micro frequency omega is in omega will be hundreds of megahertz or gigahertz. So if you multiply to the L, that will be greater. So okay, R should be much less than omega L, and G should be much less than omega C. So characteristic impedances comes out to be Z, we have formula Z naught is equal to R plus J omega L divided by G plus J omega C. So just take J omega L outside and J omega C outside from the numerator as well as denominator. So it will comes out to be 1 plus R by J omega L and 1 plus G by J omega C. So you just take J omega cancel, you get root under L by C. So you take here root under L by C. Now this can be written as 1 plus R by J omega L as power half, and 1 plus G by J omega C as a minus half. Okay, power as a minus half. So now you can take this using the binomial expansion, because R is much less than omega L. Just take binomial expansion, and this will become 1 plus R by 2 J omega L. Plus dot dot dot, you can ignore these terms, and this will become 1 minus G by 2J omega C. So if you multiply these two, just ignore all the higher term. just multiply these two, you will get 1 plus r by 2j omega L minus g by 2j omega c minus dot 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 this one. Huh? So this you can just cancel out. You can say this is to our minor values. Quite similar, because some this is connected with plus sign, this is connected with minus sign, this is associated with the plus sign, this is associated with the minus sign. So these two can be somehow it will be cancelled, and you will get z naught is equal to square root of L by C into 1. So z naught will be square root of L by C. So that is the characteristic impedance. Okay. So although lowest line and lossless transmission line both are having characteristic impedance is equal to root under L by C, but not so for the propagation constant. Here the propagation constant j omega root under LC, but there it will be, here it alpha is completely zero, but there you can see alpha is not complete zero. Alpha will be some value. Okay, although beta will be same, but alpha will be some value. So here, if you solve for the propagation constant, similar way we will try to calculate. Gamma is equal to square root of r plus j omega L into g plus j omega c. So we just take j omega L outside and j omega c outside. So you just take j omega is outside, you will get j omega root under LC, and this will give you 1 plus r by j omega L power half, 1 plus g by j omega c power half. You take binomial expansion. So using the binomial expansion. So binomial expansion, this will comes out to be 1 plus r by 2 j omega L and 1 plus g by 2 j omega. So just multiply these two, you get this term. Just ignore this higher degree term, because this omega square omega is a very higher value, and r and g is very small. So this will be ignored, and this can be 0. Now you can see here, this is r by 2 j omega L and g by 2 j omega c. And this both are positive sign, and this it is added with the 1. So this will give you some value, so you cannot ignore directly. Okay, you take this, just multiply this j omega root under LC with both the term. So we'll get gamma is equal to j omega root under LC plus r by 2, and j omega get cancelled. Root under LC divided by L will become root under C by L, and this will become g by 2 root under L by C. So this is the value which we are getting here, and this can be written as alpha plus you can write j beta. So this is alpha plus j beta. So this is the value alpha, and this is the value for beta. Beta is same omega root under LC. Beta is same omega root under LC, and alpha you are getting as alpha is equal to r by 2 root under C by L and g by 2 root under L by C. That is called attenuation constant. This is called alpha C, and this is called alpha D. Alpha D. Okay. So this alpha is due to the conductor, and this alpha is due to the dielectric. Okay, so dielectric which is present in the transmission line. So this is the attenuation constant. Okay. Now, if you go for the voltage, if you want to find for the voltage, so voltage V of Z is equal to V naught plus E to the minus gamma Z, V naught minus E to the plus gamma Z. And similarly, we have a current V naught plus divided by Z naught E to the minus gamma Z minus V naught minus Z naught divided by Z naught E to the plus gamma Z. Okay, so that's how we can calculate voltage as well as current, and gamma will be whatever we have gamma that will be there. Okay. Similarly, we have a wavelength lambda is equal to 2 pi by beta, which is equal to 2 pi by omega root under LC. Beta is nothing but omega root under LC, so just apply here. And phase velocity Vp is equal to omega by beta, which is equal to 1 by root under LC. Similarly, you can have the analysis for the distortionless line. So distortionless line, we have the condition that R by L is equal to G by C. So for the distortionless line, the condition is R by L should be equal to G by C. So you can substitute this R by L is equal to G by C, okay, wherever it is required, and try to find out for the distortion. But practically, this is also not widely used. Okay, so we widely use this lowest line. Okay, lowest line. Widely use this lowest line, and this is the lossy line. Lossy line already we have derived that equation. So equation which we have derived, all the equation which we have derived, that is called lowest line. That is called, sorry, that is called lossy line. Okay, so lossless, it will be a little bit changed. lowless is also some of the value like alpha, it will be changed. Okay. And distortionless, it will be, again, it will be changed. So you can solve for the distortionless also. Okay. So that's it for today, today's class. Okay. If you have any doubt, please let me know. Otherwise, I will stop here. If you have any doubt, please let me know.